morning grade 12 black one, correct? Okay, please stand up everyone. So we're going to start our discussion for this morning. So let's start with an opening prayer. Please bow our heads. Amen. Okay, please sit properly and make sure that you are sitting with your chair properly and ordered. Okay, now we're going to check first your attendance. So I would be noticing each one who are present in this discussion. So I will be checking your attendance. So please say "Shilos" if you are a girl and "hellos" if you are a boy. You can make any unique actions so that I would recognize each one of you. So, grade 12 STEM Black 1, Atua Trave Johnson T, Bonete Jace Ian N. Okay. Concepcion Mark Adrian C. Oh, present. Piren John Jared P. Where are you? Okay. Rosales Sambi. Good morning. Brillones Brianna Rose. Oh, she knows. Okay. Javier Akisha May R. Okay. Manalo Angeline R. No, present. Manalo Plate Chelsea. Okay. Ulit Angel Resume R. Good morning, everyone. We are having a simple motivator and brain energizers so that we'll be able to train our brain cells in neurons as we are going to have a very detailed and conceptual discussion this morning. So, I'm going to remove this. Okay, we're going to have a temperature check. So, from happy up to angry. So, from yellow-green up to red. So, I'm going to have a different rumbled words. Okay, Pete Chelsea. Oh, the first word is temperature. Oh, that's correct. What do you feel as you order the letters? Oh, you are color green. Oh, a little bit happy. Very good because it's too easy. Okay, next. Jace Ian. Okay, stand up. Oh, that is system. Very good. How do you feel? Oh, okay. I'll also color green. Oh, that's good to hear. Next. Oh, John Jared. Energy. Very good. That is energy. Next. Okay, what is this? You're having a trouble? Oh, it's red. Oh, you're feeling red this time. Okay. What is that kaya? Oh, you're having a trouble. It is entropy. So later on, we're going to discuss more about it. So please be reminded and take note of entropy. Next. Oh, it's easy. What? Oh, Brianna? Okay, that is equilibrium, correct? Next. Oh, Brianna again, okay? Heat and work. Okay, please clap. Very good. I hope you train your brain cells so that we will be able to have an energized mind as we are going to discuss the lesson proper. But before that, I want to remind each one of you to be CCC. Just like I am, my initial is CCC, Carmela Hazel, C Carpio. So what I want you to bear in mind on this class is always be concentrated, always be cooperative, and always be creative. Why? If you don't follow those rules, mag-CCC kayo. Okay, so we're going to discuss now the laws of thermodynamics. The lesson proper. So the laws of thermodynamics are zeroth law, first law, and the second law. So this law will be able to explain truly and proficiently this morning. So law of thermodynamics is defined a group of physical quantities such as temperature, energy, and entropy that characterize thermodynamic systems and thermodynamic equilibrium. So we're going to start with the zeroth law of thermodynamics. So what is zeroth law of thermodynamics? Here it is. So let's discuss what is zeroth law of thermodynamics. Can someone read what zeroth law of thermodynamics states? Okay, John Jared Peren. That's correct. So what it is being emphasized. So the system 1 and the system 2 are in thermal equilibrium with system 3. Okay, let us say that thermal equilibrium is a state of a system in which all parts are at the same temperature. So it is said that system 1 and system 2 are having or had a same temperature. So that does mean that they are equals also with the system 3. Therefore, the system 1, system 2, and system 3 are in thermal equilibrium with each other, simply that all heat is of the same kind. Therefore, the system A, B, and C had a same temperature. So, Ralph Howard Fowler is the one who formulated the zeroth law of thermodynamics. How we're going to prove, how we are going to know that it is true that system A, B, or C could have a same temperature. So we have the application. So we have the system 1, 2, or 3, or the object 1, 2, or 3. So the system 1 are hot water, system 2 cup in contact, and system 3 is metal spoon. Let me show to you. What can you see? A thermos. Okay, that's correct. A cup, and as well, see a spoon. Okay. Inside this thermos is a very hot water. So we're going to pour the hot water into the cup. Let's do it. Simple as that, like what we are doing in daily basis in real life setting. That's correct. So let's put it down. I have now a hot water inside a cup. They are in contact with each other. Like what we have learned in principle of heat transfer. What is this kind of heat transfer? What is this kind of heat transfer? Adrian? That's correct. Conduction. They are a direct contact with each other, therefore heat is being transferred. I can feel it on my hand that it's hot. So, therefore, the system 1 and the system 2 had what? Same temperature. They are in thermal equilibrium with each other. Let's put the system 3, the object 3, or the object C. A metal what? A metal spoon. Who are here? Who will be able to know what is metal spoon contain? A metal spoon is high conductors of what? Acacia. That's correct. As it is high conductor of heat, it is high conductor of electricity. So we're going to have it in contact with the hot water in the cup. Let's mix it like this, like what we are doing when we are preparing a coffee in the morning. They are in thermal equilibrium with each other. Are you agree? That's correct. The system 1, the system 2, and the system 3 are now in thermal equilibrium with each other. Therefore, it is true the zeroth law of thermodynamics. Simply as what we are doing in reality. So, who wants to have it a question? Okay, nothing? It's clear. Okay, zeroth law of thermodynamics is simply a thermal equilibrium in 3 bodies. A thermal equilibrium between system 1, system 2, and system 3. Now, let's move on the first law of thermodynamics. Okay, now that we are done with the zeroth law of thermodynamics, we're going to put a check. It's like what we are doing in a to-do list. Okay, done. What we are going to discuss now is the first law of thermodynamics. I hope you are seeing it clearly. Okay. So, the first law of thermodynamics is always associated with the energy. Who wants to read? Okay, I would read for you. First law of thermodynamics states that a change in internal energy of a system equals the difference between the heat taken in or given out by the system and the work done by or on the system. Okay, how we're going to explain this? So, the heat and work is associated with the first law of thermodynamics, where we're going to determine the change in internal energy. But first, what is internal energy? Okay, internal energy is an energy associated with the system's molecules and comprises both kinetic and potential energy. That's what is internal energy. So, it is said that a system's internal energy can be changed by transferring an energy by either work, heat, or combined. That's what is stated. And also, did you know that an adiabatic process, like what we have discussed, the thermodynamic process, is the one that associated that and also leads to the change in internal energy due to the any work done that happens via expansion and compression. That is true. Okay, it is also said that the change in internal energy is equal to measurable changes. What is means by measurable changes? It could be measured in the macroscopic variables of the system, such as pressure, temperature, and volume. So we are having here a very conceptual information. And later on, we will be having a game. So we will familiarize more to this topic. So it is said that Rodolphe Clausius is the one who formulated and also the one who defined first law of thermodynamics. So thermodynamics is equal to change in internal energy, notated as delta U is equal to difference, ibig sabihin, minus, between heat taken in or given out, symbol is capital Q, and the work done by or on the system. We're going to know what is the change in internal energy through this Clausius notation equation. Okay, so we have the postulate that says that work is equivalent to energy. That is what first law of thermodynamics stated, as well as heat is equivalent to energy. Net accumulation is equal to the increase in internal energy, and if there is net reduction, that's correct, is equal to decreasing of internal energy. For us to be able to learn more about it, I have prepared a question and a game, which is bingo, for us to be able to familiarize with all the words, terms associated in first law of thermodynamics. So here are the questions. I have here a bingo card. I will be giving you each one of you one. So please get one and pass. Okay, I have been having my own. So in this bingo card, we'll have 25 or 24 because change in internal energy is on the middle as a bonus for your performance task. So we have 24 words for you to be able to have a bingo using these 5 questions. So we're going to answer it one by one. So have please a ball pen and a card only on your desk. Okay. So the internal energy question number 1, you're going to make a triangle or the change in each word. So for example, reduction, you're going to make it a change or theta in order for you to mark it as your answer. No erasure. Okay. Number 1, the internal energy decreases if there is net blank of energy in the system. Now write your answer. 3, 2, 1. What is the answer? Adrian? Okay. Net reduction. So, kita ko ha. Okay, number 2. It is the energy that can be changed by transferring energy by either work, heat, or combine. What is your answer? Please write it down on your bingo card. Okay, I think someone has already have 2 answers correctly. Oh, that's okay. Very good. Number 3, a thermodynamic process that lead to change in internal energy due to work done through expansion and compression. What is that thermodynamic process? I have stated it a while ago. Okay, I have seen some who are wrong. I've seen some also who are correct. Let us see who are going to have it bingo. Okay, number 4, a change in internal energy results in measurable changes like pressure, or it could be temperature and volume, are called blank. What could it be? 100 points for your performance. Okay? Total energy of the universe is increasing, decreasing, or remains constant. What could it be? Guess it. Okay. What is the total energy of the universe? I have here 3 choices. Choose one. Okay, you had bingo. Okay, let's clap for Adrian. Jace Ian. Okay, I'm going to note it. Jace Ian. Oh, Brianna. Okay, Akisha as well. Sam. Okay, clap. Each one of us. Very good. Okay. Oh, let's again reflect. What is first law of thermodynamics? Talks about the change in internal energy that equals to the difference of heat taken in or given out and the work done by or on the system. Please take note that first law of thermodynamics always highlights that change in internal energy. So moving on to second law of thermodynamics. We are on the last law on this morning, the second law of thermodynamics. Who would like to read what second law of thermodynamics states? Oh, Rasha. Okay, please read. Okay. Second second law of thermodynamics states that energy is transferred or transformed more and more of it is wasted. So what second law of thermodynamics is all about? It's taking account to the lower temperature in order to do work. So it highlights the arrow of time, which is one direction in the universe and not the other. What could it be? Who wants to answer? Ray Jansen. Okay, the arrow of time or the one direction that is all about is either increasing or decreasing. So we have also will encounter the entropy and enthalpy, but some are having a trouble and double cross their minds when it comes to entropy and enthalpy. So let's differentiate. So entropy is denoted as capital S, while enthalpy is denoted as capital H. Entropy is the measurement of disorder within a system, while enthalpy measures how much energy is released or absorbed during chemical reaction. So when we talk about entropy, it's mostly related to the randomness or the disorder on the system. Like what we have all know, machines have lots of disorder, system have lots of disorder. Entropy have also a relationship with the matter. What are the matters? State of matter. Okay, solid, liquid, and gas. Gases have more entropy. Take note of it. Liquids have less entropy, while solid have least entropy. It has a directly proportional with entropy. So, gases have more entropy means it has disorder. Like what we have said that entropy is the measure of disorder. So, the liquid have less entropy means it has what? Less disorder. That's correct. How about solid? It has least entropy. It has also least disorder. Okay. As time goes by, what can you see or observe in different systems or machines? It decreases what? Its efficiency, and it also increases its disorder. Okay, that's correct. We're going to highlight that it is impossible to convert heat energy to mechanical energy with 100% efficiency. Why? Because all machines cannot function fully enough and lifetime. It has disorder. Okay, that's correct. And what is thermal efficiency? It is how well an engine operates. Here, a jar of truth. If we have an arrow of time, we have a jar of truth. I have your questions and I will going to ask each one of you. So it's time for you to have internalized what I have said a while ago. Okay, let's call Ray Johnson. Okay, what is this? What is randomness? Okay, it's also called disorder. Okay, I'm going to call each one of you. Jace Ian. What is the formula of thermal efficiency? What is the formula of thermal efficiency? It is EFF or F, it is equal to 1 minus QC or energy removed by heat divided by energy added by heat. Very good, that's correct. Next, Mark Adrian. What is the symbol of enthalpy? H. Very good, that is correct. Next, John Jared Perrin. What is enthalpy? Enthalpy, it is on the board. Enthalpy is the measures of how much energy is released or absorbed during chemical reaction. Okay, correct. And who's next? Sam P. Rosales. Differences between entropy and enthalpy. Okay. The entropy is the measurement of disorder. Okay, the enthalpy is how much energy is absorbed or released. Okay, very good. Symbol for entropy. Who's next? Brianna Rose. Entropy is equal to a symbol as capital S. Very good. Who's next? Akisha May Javier. Second law of thermodynamics. Second law of thermodynamics is all about, okay, energy is transferred or transformed, more and more of it is wasted. So it takes into account the waste heat or the work which is not or the heat which is not transformed or used into work. Okay. Who's next? Angeline Manalo. Okay, area of sciences that arrow of time encompasses. You can give one. Of course, thermodynamics. Very good. What's next? Rachel C. Manalo. Waste heat. A certain amount of heat which is not transferable or is not useful to do what? Work. Very good. And last one, Resha May Sophia. Arrow of time. Arrow of time is, what is the direction? Either, very good, increasing or decreasing. Okay, that would be all. Each one of you are correct and I am proud and thankful for your cooperation. Now, I'm going to call one for her to have a recap in here, in front of each one of us on the discussion proper. Once. Okay, Faith Chelsea, come here in front. Hello, I am Faith Chelsea Manalo. So, the topics is the law of thermodynamics, and what I have learned is that in zeroth law of thermodynamics, it is shown mostly on our daily life without realizing it. That zeroth law states that system 1, system 2, and system 3 are having a thermal equilibrium or the same temperature. And that's what I have witnessed on the actual representation using real objects. As well as here, in the first law of thermodynamics, I have learned that it is associated with the change of internal energy with the difference of the heat taken in or given out and the work done by or on the system. And on that second law of thermodynamics, I have learned the arrow of time, that the one direction is either increasing or decreasing, and also the difference between the entropy and enthalpy, which is one of those words that are hard to understand. Now that entropy is always associated with disorder, while enthalpy is on the chemical reaction is simply the how much energy is released or absorbed. And I have learned that system are not have 100% efficiency. So that would be all. Thank you. Okay, so Faith Chelsea emphasized as she have a recap and reflection of what she have learned this morning that the zeroth law of thermodynamics is always describing always all about the thermal equilibrium. That's correct. While the first law of thermodynamics is always um, highlighting the change in internal energy. That's also correct. And the second law of thermodynamics always deals with the randomness or disorder or the entropy. So let's have a hand for Faith Chelsea. Very good. Okay, now that we have understand all the concepts, also train our knowledge and skills in this topic, laws of thermodynamics, I want you all to evaluate yourself and also to learn more from this given assignment assigned to each one of you. So I want you to make a three-way Venn diagram. So it will be a very open output. You're going to be creative as you want to be in a short bond paper. So compare and contrast the laws of thermodynamics, the zeroth, first, and the second law. So I am giving you the freedom to browse online and to check references or reliable sources and credible articles, so you will be able to present a very systematic and as well as informative output. So I will giving you until Friday, so we will be welcoming a very great weekend and also waiting ahead and also welcoming Monday with a new lesson, use heat engine. So I'm giving you the freedom to have your advanced reading, so you will be able to cooperate again and also be reminded of lots of concepts that will be introduced to each one of us. Okay, so that would be all. Let's end with a closing prayer. Amen. Okay, that would be all. Thank you, grade 12 STEM Black 1. Class adjourned.